I am very happy to welcome Professor Morita. He will speak on the existence problem of compact quotients.
Thank you very much, and thank you very much for inviting me to this conference. This is my first time to come to India, and I'm very enjoying it so far, and also Happy New Year. So today I would like to talk about the existence problem of the compact quotient of pseudo-Riemannian homogeneous spaces. This is a joint work with Fanny Cassel and Nicolas Torozan. Okay, and so let me start with the introduction. Although in today's morning, Professor Kobayashi gave a wonderful lecture, so I might repeat some part. But anyway, so let G mod H be a homogeneous space. Today I will concentrate in the real case, so that the homogeneous space always mean a quotient of the real Lie group by a closed subgroup, real subgroup, and gamma is a discrete subgroup of G. And we want to construct a manifold locally modeled G mod H by taking a quotient by gamma. But in general, G mod H mod gamma can be a very pathological space. But this action happens to be a proper or properly discontinuous equivalently and free. Then the quotient space admits a natural structure of the manifold. And the quotient map from G mod H to G mod H mod gamma is a covering maximum. So that in this case, G mod H mod gamma is a manifold locally modeled on G mod H. And in this case, we call G mod H mod gamma a Clifford-Klein form of G mod H. It is sometimes just called, I think, locally homogeneous manifold or something like that. But today, I will call it a Clifford-Klein form for this kind of a double coset space. And I would like to remark that if the action is proper, then even if the action is not free, the quotient space is more or less nice in the sense that it becomes an orbifold. So it is a Hausdorff, and it is locally modeled on some Rn divided by some finite group action. But if the action is not proper, then even if the action is free, then this quotient space is a very pathological non-Hausdorff space. Like you can consider, for instance, the action of the square root z on R mod z. Then the quotient space is a very pathological space. So the properness is very essential, very essential condition. Okay, and as I explained in Kobayashi's lecture, if you are given a G-invariant geometric structure on G mod H, then you can get a corresponding geometric structure on the G mod H mod gamma, like a pseudo-Riemannian model. And conversely, in some case, if your geometric, if you're considering a very nice kind of a geometric structure, then you can sometimes prove that any manifold if this geometric structure is in fact a Clifford-Klein form. The most important example should be a space of constant curvatures. And I'm going to explain the case of the negative curvature. So let the HPQ to be this space. So the HPQ is an open subset of the real projective space, which satisfies this inequality. In other words, with our definition, this HPQ is a set of all negative definite lines in RPQ plus 1, where RPQ plus 1 means this is as a vector space, it is RP plus Q plus 1, and we put the signature P Q plus 1 indefinite symmetric Pioneer form. Okay, so this open subset in RP Q plus 1 is called a pseudo-Riemannian hyperbolic space. If Q is equal to 0, then this is just a Klein projective model of the hyperbolic space. And on the other hand, if P is 0, then this condition is vacuous, so that this is just a RPQ. And in general, it is in between. And you can see that this has a pseudo-Riemannian metric with a signature PQ, and isometry group is a projective OP plus O, a projective of OP Q plus 1, transitively on HPQ, so that you get this diffeomorphism, as in the case of the hyperbolic geometry. In the case of the hyperbolic geometry, Q is 1. And unlike the case of the hyperbolic geometry, this HPQ may have a fundamental group, so that I need to consider the universal cover. When Q is at least 2, then this is in fact a double cover, and the universal cover is this one. And in this case, you can prove that any Clifford-Klein form of HPQ tilde is a negative space form of signature PQ. Here, negative space form means that the complete Riemannian manifold with sectional curvature identically equal to -1. Because the killing form of OPQ plus 1 induces a constant curvature pseudo-Riemannian metric, which is a G variant. So that the direction from above to this middle one is trivial, not difficult. But in this case, because of the niceness of this geometric structure, rigidity, you can prove the different converse direction, as in the case of the hyperbolic geometry. And I should remark that if you want to consider positive space form, then if you consider the signature QP instead of PQ, then there is a one-to-one correspondence between this, because here you can consider, if you have a negative space form of signature PQ, and if you multiply the metric by -1, then you get this one. So today I will concentrate on this negative space form case and consider all the signature PQ. Okay, and in this talk, I would like to consider the following problem, which was already mentioned in the Professor Kobayashi's talk. So given the homogeneous space G mod H, determine if it admits a compact Clifford-Klein form. So compact quotient, often it is just called a compact quotient. So it asks if you can find a manifold which is locally has a very nice geometric structure, locally modeled G mod H, and also it is topologically nice in the sense that it is compact. And in general, this problem is very difficult and not solved for many cases. Okay, and as a special case, you can consider the case of the G mod H equals HPQ tilde. Then this problem is equivalent to asking if asking to determine all PQ pair of the natural numbers such that there exists a compact complete pseudo-Riemann manifold of signature PQ with a sectional curvature -1. Okay, and a small remark is that if G is linear, which is the case I concentrate. Today, I always assume that the Lie group G is linear, so that you can always apply the Silberg's lemma, and passing to the finite index subgroup, you can get the torsion-free subgroup. So that the existence of the compact Clifford-Klein form is in fact equivalent to the existence of a torsion-free discrete subgroup, which acts properly, co-compactly, and freely. But the freeness is automatic from the torsion freeness and the proporness, so that this condition is equivalent to this. So you so it makes life a little bit easier if you concentrate in the case of the torsion-free subgroup. Also, the problem is insensitive to passing to the linear finite covers of G or adding compact factors to H or etc. because the freeness is now not the problem. Okay, and there's a lot of approaches to these problems, and I would like to list some of the major approaches. The one is using the structure theory of the reductive Lie groups, so namely the proporness criterion in terms of the KAK decomposition of the reductive Lie group G, which I think will be explained in tomorrow's Kobayashi's talk. But anyway, so this approach is using this proporness criterion or that kind of thing, so you can get some non-existence results and existence results for the compact quotient, including the example explained today's Kobayashi talk, and also even Benoit's work, and also myself, some generalization of this Kobayashi's result. And this the systematic search for this systematic search for G mod H to which this method applies. It was done later by Okuda and Bohansky, Tralle, and I mean Polish. I mean people in Poland, not Polish. Sorry, not a technical word in mathematics. Sorry. Okay, and also there is a method using a homogeneous dynamics, like Ratner's orbit closure theorems and Zimmer's cocycle superrigidity, which first was done by Zimmer and then Labouri and Moses. And there's another method also mentioned in today's Kobayashi's talk about the infinite dimensional detail representation. Decay of the matrix coefficients gives you some result. It was first done by Marguerite, and Shalom did a different kind of result. And the systematic search for the example to which Marguerite's method applies was done by O and then Benoit and Kobayashi. This was also mentioned in today's morning's Kobayashi's talk. And then there is another method based on the cohomology, named the drum cohomology and relative Lie algebra cohomology, which I did in my PhD. And so this I think goes back to the work of Ravi Kulkarni and then Kobayashi Ono and Bruno Laburi and myself, and also the work of Nicolas Tolozan. And very recently, it is not written yet, but there is a recent work by Cassel and Tolozan based on the geometric theory, more precisely the Anosov representation theory. Okay, and the nice thing about this existence problem, the compact quotient, is as I said, there are a lot of the different methods. And also these different methods often gives partially overlapping but different results. So that it's a it may say that you can say that it shows the depth of this problem. And one can say that this problem is one of the crossroads in mathematics. Okay, and let me give one example of this problem. So the case of the HPQ, although this case was already explained in Professor Kobayashi's today's talk. So in this case, there are some PQ to which for it the compact quotient exists, namely the case 0n. So this case is so HPQ this is just the RPQ. So this is trivial case. And then N0, this is the Riemannian hyperbolic manifolds, and there always exists a compact quotient in this case. But there is two series and one exceptional example for pseudo-Riemannian setting found by Kulkarni and Kobayashi. On the other hand, there are some non-existence results, namely when Q is at least P and P is positive, then there is not exist a compact quotient. In fact, in this case, there is no infinite gamma which acts properly on G mod H. So in this case, you get a stronger result, as explained in Kobayashi's talk today, and probably will be explained tomorrow in much more detail. Also, there are some non-existent results for different values, and so this was done by Bruno, and this was done by Kulkarni, and more recently, I and Nicolas Tolozan proved some result subsumes this case and this case. So it says that P should be even once you assume that Q is positive. So this is a list of the examples. This is a list for the case of the HPQ. And today I would like to give a new non-existence results. And it is so it gives a new results for HPQ and many other homogeneous spaces. But and this is formulated in terms of algebraic topology of sphere bundles. The statement is stated in terms of some algebraic topological terminology, although the proof is in fact differential geometric. But before stating our new necessary condition, let me explain the geometric vibration conjecture, which is a conjecture picture of the geometry of G mod H mod gamma. So in the mid-2010s, about 8 years ago, I think, Nicolas Tolozan proposed the conjecture picture of the compact quotient, and which he calls the geometric vibration conjecture. And our main theorem is, in fact, our main theorem or its proof is inspired by this conjecture. So what is this conjecture? So let me explain the conjecture. So our setting is the following. So G is a linear reductively group, and H is reductively G. And suppose that you have a proper and co-compact action of gamma, which is torsion-free. So that you have a compact Clifford-Klein form, compact quotient G mod H mod gamma. For simplicity, I assume that it's torsion-free condition. And then I take a maximal compact subgroup K of G, so that the intersection of K with H is again a maximal compact in H. Then you can consider this double vibration. So you have G mod H mod gamma, but H contains a smaller subgroup K intersection H. So you can consider this vibration. And this vibration has a contractive fiber H mod K intersection H. And then this K intersection H is also contained in K. And you can consider this another vibration. So the fiber is K mod K intersection H. So this time this is a compact fiber, but this has a non-trivial topology. And I would like to remark that since gamma is torsion-free, these actions are automatically free. Gamma action on G mod K intersection H and G mod K are automatically free. And the properties is obvious because the K is compact. So these three Clifford-Klein form can be considered. Then the geometric vibration conjecture asserts that you can find some submanifold M gamma inside here. So that if you consider the inverse image of this submanifold inside here, so you consider inverse image here, then this pi gamma induces a diffeomorphism between this inverse image and this G mod H mod gamma. So in other words, this G mod H mod gamma can be nicely embedded inside. You have a nice section, G mod K intersection H mod gamma, so that this is a vibration. So let me say again. So this geometric vibration conjecture can be restated as follows. There exists a section of this pi gamma, which I call sigma gamma, whose image is foliated by K mod K intersection H, the fiber of this one. So in particular, it says that you can find a smooth fiber bundle whose total space is G mod H mod gamma, and typical fiber is K mod K intersection H. Sorry, this KH means K intersection H. Sorry for the inconsistent notation. So, but in fact, it says a little bit stronger thing because this vibration is compatible with these geometric structures. Okay, let me explain this conjecture in one example. So let us consider the case when G mod H is Hn1. So this is often called the anti-Dogit space, ADS n plus 1. So G mod H is this one. And in this case, K and K intersection H is like this. So in this case, so what is what geometric vibration conjecture says is the following. So in this case, G mod H mod gamma and G mod K intersection H mod gamma and G mod K mod gamma are respectively. So this one is just the ADS n plus 1 divided by gamma. And then here you have a based time-like geodesics in ADS n plus 1 mod gamma. Here the time-like means that this is a negative definite direction. And so this vibration is just giving a base point, assigning a base point to each geodesics. And instead, you can forget the base point and you get this vibration. So this is, in this case, that double vibration can be restated in terms of the Lorentzian geometry in this way. And the geometric vibration conjecture says that this ADS n plus 1 divided by gamma should admit the foliation by time-like geodesics. And even for ADS n plus 1, this conjecture, I think, is not solved yet, except for the case of ADS3. Okay, and obviously you can rephrase geometric vibration conjecture as follows. So instead of considering the vibration on the double cosette space, you can consider the gamma equivariant vibration on just homogeneous spaces. And you can rephrase the geometric vibration conjecture in this way. So you can find the gamma invariant submanifold of G mod K, which induces diffeomorphism from the inverse image of this one to G mod H. So I just removed the gamma here, and instead I added the word gamma invariant here. Obviously, they are equivalent. Okay, so there's some supporting evidence for this conjecture. Namely, first, this geometric vibration conjecture is true for standard compact quotient explained in Kobayashi's talk. And it is not difficult to see. And also, geometric vibration conjecture, the validity of the geometric vibration conjecture is an open condition. Namely, so you can consider the moduli space of all compact Clifford-Klein form with given abstract torsion-free subgroup. Given an abstract torsion-free discrete subgroup, gamma 0, then you can consider the moduli space of compact Clifford-Klein form with gamma equals gamma 0. Namely, you can consider the space of all discrete embedding of gamma 0 inside G so that this quotient gives a compact Clifford-Klein form and then divide it by the conjugate. So this is a moduli space of the Clifford-Klein form with a prescribed abstract discrete group. Then the set of all these point in the modular space such that the geometric vibration conjecture is true is open in M, this modular space. This is not difficult to see again. And in particular, this geometric vibration conjecture is true for a small deformation of the standard quotient. And beyond the standard quotient or its small deformation, there are two cases where the geometric vibration conjecture is known to be true. The first example is the case when G mod H is a group manifold of POM1. This is as a space, it is just a Lie group PON1, but you consider left and right action. So in this case, the validity of the geometric vibration conjecture was proved by the work of Guilito and Cassel, which is, this was published in 2017, but it was in fact done before the work of the Prasad, and I think one of the motivation for him to formulate the geometric vibration conjecture is that this is true in this case. So this predates the geometric vibration conjecture. And I would like to remark that when n equals 2, this is an anti-Dirichlet string manifold. And in this case, so when n equals 2, and let us consider the gamma 0 to be the surface group with a G at least 2, then the modular space M for this surface group is not connected. However, so this statement says that the geometric vibration conjecture is true for every point of N, including the one which does not belong to the same connected component as the standard one. Okay, then there is another example where the geometric vibration conjecture is true, namely the case of the O2N2 mod UN1. This is proved by very recent result by Monclé, Shirenka, Tolozan, and also Cassel Tolozan. This one is not published yet, and this one is put on the archive on the last October, I think. Okay, in this case, more strange thing happens. In fact, in this case, for any n at least 2, there exists a compact Clifford-Klein form G mod H mod gamma, such that this gamma is not isomorphic to any co-compact lattice of any reductive Lie group. So it is, of course, not a co-compact lattice in G because it cannot happen because H is non-compact, but it is not isomorphic to co-compact lattice of smaller group. In fact, this gamma is something called a fundamental group of the Gromov-Sarson manifold. And in fact, for n equals 2, 3, 4, then this kind of example was earlier found by Lee and Maki using by constructing some strange Coxeter group. But their method is more geometric. In any case, so there are some very strange quotients, but this condition 4 says that the geometric vibration conjecture is true even for such very strange gamma. But besides these examples, the geometric vibration conjecture is widely open. In any case, so this geometric vibration conjecture should imply some general result for the existence problem compact quotient, namely, if you write n as a normal bundle of this compact homogeneous space K mod K intersection H in G intersect G mod H. So this is a normal bundle. Then the geometric vibration conjecture implies that G mod H admits a compact Clifford-Klein form, compact quotient, only when this normal bundle is trivial as a vector bundle. In fact, this statement is in fact conjecture by Kobayashi and Yoshino in mid-zeros, but the point is that this geometric vibration conjecture, which is some conjecture about the conjectural picture of the geometry, should imply this condition. And the proof is not difficult because so if you believe the geometric vibration conjecture, then you get the vibration like this. And we, in fact, do not even need the gamma equivariance of M. You can just say that you can find some M whose inverse image is diffeomorphic to G mod H. Then you look at this inverse image rho inverse M, which is diffeomorphic to G mod H. So this is a picture inside G mod K intersection H. So this is something like this is a G mod H. And here you have n, and you look, then let us look at the 1 point and look at the inverse image. An inverse image is identified with k mod k intersection h. And since this is 1 point, that normal boundary is of course trivial, so that it's pulled back. So here again, the normal boundary should be trivial. So this is not that difficult. And then let me state our main result. So our result is that without assuming the geometric fibration conjecture, so we do not assume the geometric fibration conjecture, and we prove a somewhat weaker statement than the previous, this one. Okay, what is the result? So our result is the following. So let G, H, K, and N as before, and let us consider a unit sphere bundle for this normal bundle N. Then G mod H admits a compact Clifford-Klein form only when the following happens. So only when this sphere bundle has the same fiber homotopy type as the trivial sphere bundle on K mod K intersection H. So this condition is somewhat weaker than saying that N is trivial as a vector bundle. So this is a homotopical statement instead of the vector bundle isomorphism thing. So it's somewhat weaker, but not really very weaker. It is still a very strange constraint, as I will explain. So what is a fiber homotopy type? So suppose you are given a topological space B, and suppose you are given two topological space over B, namely just continuous maps to B. So these two continuous maps have the same target space B. In this situation, you can define the concept of the continuous map over B, which is just a continuous map compatible with these projection maps. And then you can define the concept of the fiber-wise homotopy, which is just a homotopy, but everything respects the projection to the B. Then you can define the concept of the fiber homotopy type just by, like, as in the case of the usual homotopy theory, but everything respects the projection to the B. So you have a unit sphere bundle here, and this sphere bundle has the same is five at the level of fiber-wise homotopy. This is the same as this boring one. This is our condition. Okay, and how different this condition and triviality as a vector bundle? Well, you can show that if this sphere bundle is C1 trivial as a fiber bundle, then you can show that it is in fact trivial as a vector bundle. But there is a difference. There might be a difference between the C1 triviality and the C0 triviality. Although I don't know if there is in fact a difference between two in the situation of the G mod H. But then there is a difference. There indeed a difference between the C0 triviality. So this is a classification up to homeomorphism, and this is a classification up to homotopy. So there is a difference. But the easiest counterexample is something like U24-2, something like that. So this is not a very big difference. Okay, so our main theorem is that the existence of a compact Clifford-Klein form So our main theorem says that if this Sn does not have the same fiber homotopy type as the trivial bundle, then this G mod H does not have a compact quotient. Okay, this is a statement, and let me give some application. Okay, let me first mention the case of the constant sectional curvature case, space form case. So let G mod H be a HPQ. In this case, this K mod K intersection H is RPQ, Q-dimensional real projective space, and N is a sum of the P's copies of tautological line bundles. And in this case, the problem of the fiber-wise homotopy was computed, in fact, in the work of Ananas in 60s on the paper Vector Fields on Spheres. So in this situation, this Sn has the same fiber-wise homotopy type as a trivial vector sphere bundle if and only if P is divisible by some number. So this HQ is almost the half of the Q, but it depends on the Q mod 8. So in fact, he solved the vector fields on sphere problem by first saying that the existence of these vector fields ensures that having the same fiber-wise homotopy type as this one, and then deduce this condition, and then conversely, this condition would imply the existence of the vector fusion spheres. In fact, he factored this statement in his proof of the vector fusion sphere problem. Anyway, in any case, what we need is equivalence between these two conditions. And what we get is, so this HPQ admits a compact Refoudot-Klein form only when this P is divisible by H to the HQ. Namely, P and Q belongs to this list. So in today's morning talk, Professor Kobayashi says this result, its tangential analog was proved in the work of Kobayashi and Yoshino in 2005. But now we have proved a similar result for reductive original setting. Although we only proved the only when part, and we do not know if the converse holds. And if we believe the conjecture mentioned by Kobayashi in today's morning talk, then we cannot expect the converse direction, but we don't know. In any case, except for these cases, there does not exist a compact quotient, or equivalently, there does not exist a compact negative space form of signature PQ. Okay, so this is previously known cases, but we have proved new results. And in fact, that list includes all the previous non-existence results. Although there are some unsolved cases. Okay, and we were able to also solve the case of the SLMK mod SLMK with K equals R or C or H. In this case, there does not exist a compact Refoudot-Klein form for any value of n and m. But in fact, today's main theorem gives a solution to all cases but these two special cases. The problem is that in these two cases, the problem is essentially that so RP3 and RP7 has trivial tangent bundle, which comes from the quaternions and octonions. And that's a problem, in fact, so that we cannot apply our method to these two special cases. But fortunately, very recently, another method by Cassin and Tolozan solves all the cases where n equals n plus 1, including the case of these two. So we have two complementary new results so that we can now solve this. Okay, and let me mention another example, which is contains the first example of HPQ as a special case. So let G mod H be a simply symmetric space, namely let G be a simple Lie group, real Lie group, and let us consider a fixed point subgroup by some involution. So we consider this simply symmetric space. And I assume that this H is non-compact because if H were compact, then G mod H is just a Riemannian symmetric space of non-compact type, which of course has a compact quotient. And also, of course, we need to assume that this involution is non-trivial. Okay, in this case, there are some examples of the G mod H which admits a compact quotient, 5 series and 5 exceptional examples. So this is a case of the H2 and 1 anti-de Sitter case, and also H4 and 3 and H87. But there are some other examples where the compact quotient exists. Okay, but are there any other examples? Well, our new non-existent results, together with the previous results, proved the following. So let G mod H be a simply symmetric space and does not belong to the previous list, so that we don't know if it admits a compact quotient. Then we were able to prove that this G mod H in fact does not admit a compact quotient, except possibly for the following 4 cases. I mean, combined with the previous results and our new method, we were able to solve all the existence problem for symmetric space case, also simple, except for these 4 cases. Namely, so this first, second, and third cases are very similar. This is just R, C, H. And this one is the space of all negative definite Q-dimensional subspace inside R, P, Q plus Q prime. So this is a generalization of the HPQ to the Grassmannian, and similarly for this complex and the quaternion situation. And you can get, as in the case of the HPQ, that this P is divisible by subnumber, but we cannot solve all the cases. And there is one other example to which we could not solve and the previous method do not work. namely SU and N mod S will start to N with N. Okay, and this statement was proved by a case-by-case algebraic topology computation, which is, at least for me, it was hard. I mean, we use KO theory and Adams conjecture on the J group and etc. So it uses a very algebraic topology up to 60s and 70s, but still difficult for me or our group, for us. Perhaps it is easy for nowadays algebraic topologists, but I don't know. Anyway, so the proof computation is non-trivial. But in any case, we managed to solve, we managed to check all the examples, including all the exceptional Lie group case. Okay, and I would like to mention that if we could prove the C0 triviality of N, which is stronger than the homotopical triviality of Sn, sorry, this should be Sn, not N. Then the cases 3, 2, and also 1 with Q prime at least 2, these cases would be excluded, would be solved. If furthermore we could prove the geometric vibration conjecture, then we can, furthermore, we can exclude the case of the 4. But even if we could prove the geometric vibration conjecture, the case of the 1 with Q prime equals 1, namely the case of the HPQ with P and Q does not satisfy our condition. This case cannot be solved even if we could solve the geometric vibration condition. So in some sense, this case is the most difficult case. And I should also mention that although our new method is quite powerful in many situations, it does not cover some easy cases. Like, for instance, our new method does not cover the case of the G mod H equals GL for R mod GL3 R times GL1 R, basically because in this case, the quotient manifold is, in this case, K mod K intersection H is RP3 and N is its tangent bundle, and the RP3 has a trivial tangent bundle because it's just a SO3. Although in this case, you can use a very wide variety of the previous methods. So our method is strong, but it does not cover all the previous example, as I said in the introduction. Okay, I think I still have 10 minutes. Okay, let me mention a few words on the proof. Okay, what is our main theorem? So let G be a linearly reductive Lie group, and H is a reductive subgroup in G, and take a maximal compact K inside G, and so that K intersection H is again maximal compact. Then we take a normal bundle of K mod K intersection in G mod H, and then take a unit sphere bundle for this normal bundle. Then our statement is that our main theorem is that G mod H admits a compact Clifford-Klein form, compact quotient, only when this Sn has the same fiber homotopy type as a trivial sphere bundle on K mod K intersection H. Okay, let me give a sketch of the proof of main theorem, although we do not explain the most technical part. Okay, so let me first remark that this N normal bundle can be written in this form of the homogeneous vector bundle. Namely, it is associated with a representation of K intersection H on P intersection Q, where P is a orthogonal complement of K and Q is orthogonal complement of H in G, with respect to, say, Killing form, or in the case where G is reductive but not semi-simple, then you need to take some non-degenerate G invariant symmetric binary form. But I mean, yes. So this N can be written in this form, and this acts by adjoint action. So this is not difficult to see. And then this normal bundle N is in fact diffeomorphic to G by this obvious map. I think this statement in a general setting was proved in Kobayashi's work. So this is, I think this is something like a global version of the tubular neighborhood theorem. So this is a normal bundle, but usually what you get from the tubular neighborhood theorem is that the normal bundle is diffeomorphic to some neighborhood of this N. So this K intersection, K mod K intersection H. But this time you get the global diffeomorphism. Okay, you have this one. But I should remark that this map is just K equivariant, not G equivariant, because you don't have a G action left this codomain of the map. Domain of the map. Okay. Anyway, so we want to construct fiber homotopy some map between this one and this one. And for this, we take some section of this pi, gamma equivalent section, sigma of this projection. So this double fibrilation is the one we consider in the formulation of the geometric fibrilation conjecture. And the statement of the geometric fibrilation conjecture is that there exists a good gamma equivalent section satisfying some good property. But now we take an arbitrary gamma equivalent section of this pi. We take arbitrary one. But I should remark that we can always take a gamma equivalent section because the fiber of this fiber bundle is H mod K intersection H. So this is contractible. So this does not have any homotopical obstruction to get the section. Okay, so you get the section, this sigma. And then you consider the lift of the subspace of G mod H. So inside G mod H, you have P intersection Q. So this one is from this point of view. This is so G mod H is identified with N. Then this P intersection Q is a fiber at one point. And on this part, you can get the lift of this sigma because this time this basis space Q intersection P intersection Q is contractible so that you get this lift, further lift. Then we define this large phi to be the map from the trivial bundle over K mod K intersection H to G mod H, which can be identified with N. So you have a point of K intersection K mod K intersection H small x and a point in P intersection Q. But we have constructed the map from P intersection Q to G. So this large x yields the element of G. And you can multiply, you can consider the left multiplication by the element of G so that you can define this map. And I remark that this map is not very good because it is even not compatible with the projection onto the K mod K intersection H. But, you can construct, in fact, from this phi by somehow deforming or to get actual fiber-wise homotopy equivalence from this map. Here you use the co-compactness of the action as well as a property that this section is gamma equivalent. So I hide all the important geometric argument in, but idea is like this. Okay, I think I still have 4 minutes, right? Okay, then let me give some additional remarks before saying thank you. Okay, one remark is that you can rephrase the problem of the compact quotient in some situation to the problem of the Anosov representation, which was recently studied very extensively. So I do not explain the definition, but if you are given a semi-simple Lie group or maybe a reactive Lie group, and if you are given some parabolic in G, then you can define some concept of the P Anosov subgroup of G, which is a discrete subgroup with, whose dynamics on G mod P is nice. This concept was first introduced by Laborie and Guichard-Mina. And there is it is known that the concept of the Anosov subgroups, Anosov representations, and purportness is related since the work of the Guilito, Guichard, Cassel-Mina. And in particular, in the case of the HPQ, you can prove the following. So let gamma be a discrete subgroup of POP Q plus 1, and we assume this condition, this one. I mean, this is harmless because if this condition is not satisfied, then we have already proved the non-existence by previous methods, or existence or non-existence by existing methods or previous methods. Then this quotient is a compact Clifford-Klein form only when this gamma is PQ Anosov inside this group, and the cohomological dimension of gamma is P. The direction from the below to the above is the work by Guilito, Guichard, Cassel-Mina, and the compass direction is recently proved by Cassel and Torozan. So I think some of the participants knows about Anosov representation that you might find more tractable, this concept. Okay, another remark is that the simplest unsolved case for HPQ is the case of the H42. So this case is the simplest unsolved case. And in this case, there is a special subgeometry of H42. So for simplicity, I take a universal cover. So in this case, this is O43 mod O42, and it has a subgeometry G22 mod SU21. So this is a diffeomorphic for the natural inclusion map from this non-compact area form G2 inside O43. So this diffeomorphism is a non-compact version of the existence of the almost complex structure on the S6. And in fact, we do not even know if this is G22 mod SU21. So this has a smaller G, although the space is the same. But we even do not know if this admits a compact orthogonal form. And the very naive hope is that maybe this H42 actually admits a compact orthogonal form. We have proved the non-existence results for a lot of examples. Like we have proved it for all but 4 series for the simple symmetric spaces. And if you want to now construct a new existence result, if you construct a new example, then I think the natural target would be H42. Okay, thank you very much.
Thank you, Morita. Thank you. Any questions?
Regarding the group gamma, is it known or conjectured that gamma must be a lattice in maybe some other semi-simple league? Or
No. In fact, yes, this work proved that this is not the co-compact, but also not the.
So what is it then?
Sorry?
What is it then?
This one? It is something called a fundamental group of the Gromov-Sarson manifold, which is obtained by taking a branched cover of the hyperbolic N manifold. So it is so you take a branched cover so that you have some singularity, but you can fill correctly to get some strictly negatively curved but not hyperbolic manifold. And for such a manifold, you can construct a representation into the larger group O2 and 2.
How do you know that it's not a co-compact lattice?
I think by some rigidity results. I don't know. You mean that it is not the co-compact lattice inside?
Inside some Lie group. So
I'm afraid that I have never read proof of that, but I think you can use some rigidity results to exclude a possibility like that.
It's Wang's finiteness theorem. It's Wang's finiteness theorem. So because it's a Gromov hyperbolic group, so it would have to be a lattice in SON1.
We thank Morita again for a very nice talk.